I'd like to welcome everyone to this month's installment of the ReproNIm webinar. It is our pleasure to introduce Guray Erus from University of Pennsylvania. He is the Director of Research at the Center for Biomedical Image Computing and Analysis. His research is involved on neuroimaging pattern analysis that aims to detect, quantify, and analyze spatial patterns of structural brain changes due to both pathological and non-pathological processes using high-dimensional MRI image data and advanced machine learning and statistical analysis techniques. He is recommended and delivered to us via conversations with Christos Stavratsikos, who I have known for a very long time, going way back, and will present his work and their work together on the NiChart platform. And so without further ado, I will turn the platform over to you.
Thank you very much. Thank you very much for inviting me for this presentation. I'm Guray Erus. I'm a Director of Research at ABLE Civica UPenn. ABLE is a artificial intelligence in biomedical imaging lab. It's a lab that is specialized on machine learning, AI, pattern analysis on MRI imaging data. First of all, I would like to mention I knew the ReproNIm group many years ago, and I really appreciate the work this group is doing. I think this is valuable, and I'm a big supporter of reproducible neuroimaging, and I believe that the field will benefit a lot from this. So thank you very much to start with. Today, I will present NiChart, neuroimaging chart of AI-based imaging biomarkers. The story of NiChart started with when we noticed that in the lab, we have developed many methods, mainly AI and machine learning methods for detecting imaging biomarkers or imaging patterns associated with different neurodegenerative diseases. And we noticed that the utilization of these methods were restricted by multiple factors, including installation, deployment, processing power, or simply scripts that are not designed to be used by a large audience. So the idea behind NiChart, the motivation was, can we create a framework that will allow users without deep technical knowledge or without computational power to apply both image processing and machine learning applications on their data in a user-friendly platform. I would like to start with why we need these tools. I believe the context is very clear. We have a rising number of neuroimaging projects and MRI scans. Here, this simple plot shows the increase of MRI exams and number of scans per year. And I think now the number of available imaging data is very high. While there are limitations in terms of data protection issues, the number of MRIs is rising both for research studies and non-research clinical data. And I believe more automated tools are necessary for a paradigm shift in the paradigm change in the field. I believe a second aspect of the need for this paradigm change is the latest advances in AI and mainly deep learning methods. In my lab, we observed this very clearly. Deep learning methods provided significant increase in accuracy in most common problems, but also more importantly, they provided significant increased speed in application of very complex pipelines. Here I show a few examples. I think the top one is an interesting one. It's a pretty recent one. An AI-based breast cancer detection, which was tested on a very large public data set in Sweden. And actually the AI methods detection was very accurate and comparable to clinicians. So I think there is definitely a room for improving the clinical outcomes, if not by replacing doctors, by supporting their decision making. I think that's an important perspective. But also, the other article on the bottom is the human and artificial intelligence collaboration helps to reduce the workload in medical image interpretation. I think for radiologists, the future will be AI assistant, and AI-assisted radiology will definitely make a difference from the standard traditional radiology. And I believe in the research field also we will see more and more advanced AI and deep learning methods becoming standard tools that are widely applied on imaging data. Based on this context, NiChart, neuroimaging chart, as you see on this illustration here, is based on a simple idea. We have a set of reference data, a large reference set that was carefully collected and curated. This data set comes from multiple public or non-publicly available data sets. We use this data to apply various image processing and machine learning models. We provide a set of image descriptors, features, and a set of imaging biomarkers. And NiChart provides all the reference data, methods, and models to the user by allowing them to pass their data through these pipelines and come up with what we call the neuroimaging chart. As you see in this illustration, the neuroimaging chart is a simple panel similar to growth chart, pediatric growth charts, that summarizes the complex imaging data with a set of biomarkers or imaging values that are informative for associations with disease, aging, or any type of neurodegeneration. And importantly, again, similar to pediatric growth charts, our objective is also to provide reference data so that people who use NiChart can put their neuroimaging chart with context by comparing to reference distributions. We have a few basic principles in the design of NiChart. First, we aim to have a framework with near real-time image processing. So deep learning is fundamental in satisfying this aim. So we try to make our image processing and subsequent machine learning modeling pipeline steps run in near real time. We want to have continuous integration of new pipelines, methods, and AI models. Actually, we are currently working on a big update. Hopefully, we'll have a new release very soon that is making the framework more generic. Here, the objective is to be able to add a new model or processing step without changing the framework or without additional code, but just doing it by some definition files and some structured, systematic protocol. Extensive training and validation on large and diverse data sets is critical for NiChart, because one of the resources NiChart provides is a huge reference data set in the background, which is not accessible to be shared with the public because there are restrictions on some of the data sets. This data set was collected through time, and we share this data through machine learning models and reference distributions, so summary distributions of the different imaging variables. We want to have an intuitive and effective reporting and visualization. We are still working on this, and it's improving. Hopefully, in the next update, there will be major changes. And finally, optimizing the deployment, because we want the users to access NiChart pretty easily using their browser or a simple installation. I want to give an example of real-time image analysis emphasis here. In our lab, we had, I think, many years ago, a multi-atlas segmentation method we call Muse. Actually, this method was the state of the art at that time. We had the first rank on MICAE segmentation challenge. And this method was quite novel at that time. It was replacing the single atlas traditional registration-based segmentation by multi-atlas registration. And we generated a fusion of different atlases that were obtained by registering more than 10 different atlases and using 2 different registration algorithms. This method was very accurate because this multi-atlas idea works very well to eliminate errors in single registration. So it's very robust. However, it is very time consuming. So image registration is a typically difficult optimization problem. Methods like ANTs or DRANs take at least half an hour for a single image. So running 20 image registrations in serial will take 10 hours for processing a single image. We run these algorithms in parallel. So for us, the computational time was not an issue. But for the end user, this is a limitation. So for example, we replaced this model, like Muse segmentation, with what we call DL Muse segmentation. This is our new method. And the idea was simple. We run Muse segmentation by using the computational power we have in our lab for segmenting. Is there an interruption on the connection? Because I had a message about the internet. Can you hear me well?
We can hear you. Every once in
Okay.
a while, there's a little dropout, but
Okay,
it's
I had a
pretty short. So
quick message. I hope the internet connection will not be an issue. If it happens, I may try to switch to like a different computer. So at the end, the Muse was trained on labels that were created by the Muse algorithm using hundreds of computation times. And training the deep learning model also takes weeks. But now the Muse can be run in seconds on any image. So we have a segmentation of the image in seconds. And these days, there are many deep learning-based segmentation algorithms using different strategies. Our strategy was to collect a large set of pseudo ground truth data label set. There are other methods who are doing this in different ways. But at the end, in our validations, we have seen that this deep learning-based segmentation was obtaining segmentations as accurate as the original method that was computationally very expensive. So now in NiChart, we can segment an image in seconds, which is an important objective for our purposes. A second step is data harmonization. Actually here, when you work with large data sets, it's important to harmonize the data because the data comes from different scanners and sites, and it shows variations. Here, I want to show you, this is our NiChart Neuriomaging chart webpage, and all this information is provided there. So for example, for NiChart, our data set comes from multiple research studies. And within these studies, there are also site scanner differences, different manufacturers, and other variations. And this is bringing a problem, how to manage the site and scanner differences. Actually, we have 2 paths for it. One is training models that are robust to scanner differences. This is one alternative path we are currently working on. So without any harmonization, generating imaging biomarkers that are robust to site differences. I think this is a very exciting research area, and I believe that the future will be more on the modeling side, so that harmonization will be replaced by models that are robust. But another path for us was to apply statistical harmonization. And for this, we obtained the combat family of harmonization. I'm not sure if you are familiar, but combat method was initially used in the genetics field because there are a large number of variables that are harmonized. So it is a harmonization technique that is harmonizing multiple variables by setting a hyperparameter to regulate the harmonization So it's a univariate, it's a mix between univariate and multivariate harmonization. But at the end, Combat provides data sets that are aligned together. And here there are some illustrations. So I think here, for example, the Combat, after application of Combat, the batch effect is neutralized. So Combat gives results where the side effects are mitigated as much as possible. So we, let me go back to the presentation. Okay. So we apply harmonization to our large reference data set with almost 80,000 scans. And this gives us a reference set where the scanner side effects are mitigated as much as possible on the imaging variables. And here, I think this is another summary slide showing the imaging data. Importantly, our imaging data includes structural, functional DTI images of large samples with different levels of availability, because structural imaging is more available, but functional and DTI images are much less. And importantly, we carefully curated the clinical data. So in the non-imaging data, we have a large panel of disease-related variables. So these variables include cardiovascular disease-related risk factors, data, other diagnostic labels for different subsets of data, like traumatic brain injury, psychosis, depression. So we try to include into the NiChart data set multiple studies with target disease groups. And the idea of NiChart will be to include biomarkers that are specific to different diseases. An important focus of our work is on machine learning-derived imaging signatures. Actually, this is where our lab is specialized and our research is focused. We develop methods for image processing, either segmentation or deriving tissue density maps in a common atlas space, or different types of parcellations for identifying structural, functional, or diffusion-related brain parcels. But all this initial image processing step is used in a second step of machine learning-based pattern analysis. A group of supervised indices, we call them SPARE scores, are, I would say, more traditional. The idea is to use known outcome labels to train a predictive model. For example, our SPARE AD score for AD prediction capture Alzheimer's disease like brain atrophy. And importantly, SPARE AD score validations have shown that the score was also predictive of future change in MCI subjects, which is the real value of these scores. So these supervised scores trained on non-patient and control populations, they have also predictive value before the disease diagnosis is readily available. And we have similar supervised scores. For example, a recent work that was published in Nature Communications is cardiometabolic risk factors. In this study, a postdoc in our lab generated 5 different scores in the direction of smoking, hypertension, hyperlipidemia, obesity, and then this creates a dimensional system where you see different risk factors for a group of subjects. And you see that while there are overlaps between these diseases and the expressed signatures, there are also differential patterns that are very informative. Another type of methods we are working is semi-supervised. So the idea is not using the typical binary patient versus control labels, but looking for image-based, image data-driven subtypes of a specific disease. So we had a deep learning-based methods recently again published in Nature, for example, identifying 5 different aging subtypes. And similarly, we identified Alzheimer's disease subtypes. And importantly, these subtypes, because there is no ground truth, we do validations looking at clinical, cognitive, and genetic covariates and associations. And after identifying the subtypes, when we look at the expression of these subtypes on large external samples, we see that these subtypes, they make sense in terms of the imaging patterns observed, but also they show very differentiable associations with cognition, genetic, or other disease-related variables. So this subtyping approach, for example, gives us 5 scores, just to illustrate how it can be used in NiChart. So for a given T1 weighted MRI scan, we do not only calculate an AD like brain atrophy score or brain age score, but we also provide a cardiometabolic risk factor panel with 5 variables, and also another 5 variables that show the expression of 5 brain aging subtypes. Here, this is the serial gun, the method I described. And on the left panel, you see this imaging profile of this pattern. So when you look at the imaging profiles, and this is done post calculation of the score. So we have a method for identifying these subtypes. And after this identification, we look at the expressed imaging patterns on an external sample. And you see that these aging patterns show differentiations. Some group showing some more widespread atrophy, while some more temporal, and some more similar to dementia type atrophy. And this is, as you can see, quite exploratory because there's no ground truth, but it gives you a different summarization of the atrophy patterns in the brain that is powered by the large sample that we have collected and curated and processed. And then NiChart aims to provide users a visualization of these extracted values. I will show some, I will make a quick demo on this in a while. And actually this visualization component of NiChart is a moving target. We work a lot on making it easier to use and also more useful for different purposes, because a researcher's purpose may be quite different from a radiologist's purpose. So we try to find different use cases and adapt to different use cases. And for this, actually, we have surveys on our webpage. If you can visit our survey and fill out our surveys, we will really appreciate it. At the end, I will show any type of feedback will be very valuable for us. But as you see here, the visualization combines numeric data that is coming from the image processing. And this numeric data includes 2 types of data for now. One is image variables derived from processing. Typical example is volumes of segmented regions. And the second set is summary biomarkers, or we call them brain signatures, different signatures for different types of disease and conditions. For example, AD-like signature or brain age signature or hypertension signature. Of course, each signature has a different level of accuracy depending on the test. For example, AD-like signature is pretty accurate, and AD, because AD patterns are very different between AD and control subjects, while other signatures may be weaker because the pattern is not that strong. Here we have the plotting panel that allows users to see different variables together. And we also connect it with the processed images. So you can select a subject and you can see the specific region that is segmented. So you link your data to the processed images. Finally, we have an emphasis on deployment. We have 2 versions of NiChart. One is on the cloud using an AWS implementation. And one is the desktop app. Actually, the current desktop app is an installation version, which we now update with a container-based version. We have a Python-based installer, but recently we decided to switch to a completely container version because it is much more closely integrated with the cloud app. So we expect that in the next release version, the cloud and desktop will be seamlessly integrated. And this is the NiChart team. We have many people in the lab who contributed to the development of NiChart from our core lab and also collaborating lab. And now I would like to show some like quick demo of NiChart, but if you have any questions, I will be happy to answer your questions first.
I guess I will throw out, for the fun of it, a real quick question while you're switching there.
Sure.
You talked about that you use fMRI or functional types of measures. Can you say if that's resting state or task, or what types of functional MRI content might be in there?
Oh, great question. Actually, this is something which is in our roadmap and which is being prepared in the background, but it's not yet available. For fMRI processing, we use containerized pipelines from Ted Satterwhite's group. This fMRI, like they have this XCP engine that is based on fMRI prep. So our plan is to use this readily available, widely used containerized pipelines, and NiChart will be built on the outcomes of that. So now we are working on running these pipelines on our large fMRI set. It's not 80,000, it's much smaller, but we have, I think, around 5,000 fMRI scans. And we are now preparing our harmonization of these features. Actually, we have a few more steps to summarize these features with some networks. Like we apply some new algorithms like PNet for identifying individualized networks and their coefficients to reduce the dimensionality. And then this will be harmonized and we will push them to machine learning models. This is work in progress, but once this is done, it will allow people with the similar fMRI processing to push their results to the machine learning pipeline. Actually, we also plan to make this fMRI processing part of NiChart, but this pipeline takes a lot of time. So, technically, I'm not sure if it makes any sense to process it on the cloud. I think that's not very feasible. And for desktop, it can be installed and run, but we are working on how to make this integration in the most smooth way. Does this answer your question?
Yeah, thank you.
Yeah, but thank you very much for the question, because we want to have this multimodal aspect of NiChart there active, but we wanted to give the priority to structural because there is a lot of work for setting up the framework in NiChart. And once this framework is set up, adding new models, adding new processing will be something more straightforward. And while doing this, structural for us was a great target because real-time processing, real-time application was very tempting.
Yeah, great. Jacob, are you looking for a question?
Quick question. So thanks for the presentation. Could you elaborate a bit on the role of continuous integration in NiCharts? Like, do users provide new pipeline containers and then these are crunched in their own CI run? Or do they provide containers to you and that's in your central CI run? Or
Sure, great question. First thing, disclaimer, in the current NiChart, there is no continuous integration. This is something we did in a quick way, and now in our next release version, we plan to update it. And the way we do it we didn't want to generalize things too much because we don't want this to be a bag of applications. So the model we use is first, the pipeline selection and application is done based on some description files, YAML files. So every process step is defined with a YAML file, clearly indicating input-output dependencies and models and other useful information for running it. And then the pipeline selection and application is automated using this structured description format. But for adding a new pipeline, we don't want users to do it on their own. What we want to do is, for example, if you are interested in adding a new image processing or machine learning application in NiChart, we want you to contact us. We will provide you some guidance on our requirements, and then we will use it as part of it and hope, like, we want to make this integration easy on our end, but we don't want to bypass this iterative process completely, because our objective is also to verify how it runs and verify the results and then release a version with this additional component. This is our plan.
Okay, thanks.
Thank you. Should I continue with?
Yeah.
Okay. Again, I have a quick demo, short demo, and this demo again is on the current version of NiChart. That will change a lot in the next version. I will say we learned a lot in this process. While we wanted to be principled and we said, hey, let's do things properly. There is always something that you learn down the road and you may need to update your plan. So I think that some of the current components will be changed in a very positive way in the next version. And I think the direction of these changes will be more automation, more generic, and less hard-coded components. So we have this Neuriomaging.com webpage. You can find most of this information there. And there you have a link to the NiChart cloud that requires creating a login, user login. And actually here, I think here, please, if you connect to NiChart cloud, we have 2 surveys. I will really appreciate if you can fill out our survey. This is very useful feedback for us.
Are we supposed to be seeing a screen right now?
Oh, sorry. I stopped screen share, right? Yes, definitely. Thank you for the reminder.
I was imagining it for a while, but eventually I couldn't imagine the survey. So
yeah, you are seeing my screen now, right?
yeah.
Okay. So maybe I should go back to Neuroimaging chart webpage. So we have neuroimagingchart.com is our webpage. Here you can find all the information, and then there is the link for the cloud there. The cloud requires login, but when you go there in the home page, you have 2 surveys. If you can fill out these surveys quickly, we will appreciate. Feedback is always appreciated a lot. I want to show here like the current pipelines that are available. And here you see we have DTI and resting state, but these are in progress. So we don't have these pipelines readily available yet. So on the SMRI biomarkers is a test bed for us where we are putting different pipeline steps together and we test how they work on the cloud. For the SMRI pipeline, as I mentioned, the current pipeline includes segmentation of the brain anatomy, harmonization, machine learning indices, including AD, brain age, and CVR, cardiovascular risk scores, and then this additional subtype indices coming from semi-supervised models. We have a tutorial with even some quick videos that show how it runs, so you can quickly go over the videos for an overview. And we have for the timing a simple DICOM to Nifty conversion, but this is also something we plan to update. This provides you an interface to convert your DICOM images to T1 Nifty images or any other modalities. And we plan to update this with a more integrated conversion tool. We have a lot of discussions on making NiChart a complete bits app, and also connection to PAX server or other servers that provide directly DICOM data, and collecting this data in a more structured format. And the Erus segmentation is the method for segmenting images. You need to select an experiment, and here I want to select let's select a new experiment. Let's call it test 5. Okay. I want to upload my images, and drag and drop should work like that. Here I have some example images. I think these are from ADNI, if I'm not wrong. Okay. Okay, the images are uploaded here, and then I say run the Erus. Okay. The Erus algorithm consists of a few steps. Images are reoriented to a standard orientation. Then we have a deep learning-based method for segmenting the ICV, intracranial volume. So this is a brain mask that is getting the intracranial volume with the cortical CSF. And then the Erus is applied on this image for segmenting the regions. While this is running, the ICV segmentation is done, and now the Erus is running. Maybe I can wait so that we see how long it takes in the real time. And actually, these algorithms, there is a little bit of an overhead for the cloud run. We also try to work on how to reduce this time. So the segmentation is done. So as you see, it's not real time. Can I say near real time? Let's say so. But at the end, the segmentation of these two images works pretty fast. So I didn't need to leave the screen. And I'm okay to wait this much time. And we try to optimize this time, both in terms of parallelization and also reducing the overhead time, because some of the time is related to loading the container, loading the models, and so on. So now we can see the volume. So this processing gives us a CSV file with all these values, and the indices here are coming from the imaging. Actually, the image segmentation creates indices from 0 to 255. These are segmented regions. Every index is corresponding to an anatomical region, but we have also composite regions. So, for example, 601 is the total gray matter. So we combine them also into larger regions that are obtained by combining single ROIs. So when we say view scans, we need to select the ID of the subject, and we select the ROI. Here, the dictionary is applied, and as you see, I have a large set of regions. And I don't want to take too much of your time, but here, these are all derived ROIs. From here, we have the single ROI. These are the single regions, deep structures, ventricles, and then a set of cortical, it starts from here, yeah. A set of high level, we have larger and larger combined ROI. So for example, if we take gray matter, hey, this is the gray matter segmentation on my input image. And we can see it with and without the overlay. So the image segmentation is done. And if we want, we can select, let's say hippocampus. Yeah, let's look at the hippocampus for this subject, because I think this is from ADNI. Yeah, okay. So we have here the hippocampus segmentation, and I believe this is an AD subject because I see some atrophy in the hippocampus. So we have this segmentation run on the cloud, and I have my results. from here, we can continue with like machine learning biomarkers, calculate spare scores, AD-related scores for this, and then I can view the data. But I want to switch to the desktop application, if you don't mind. So here, this is our installation versions. I'm running the application here. It opens in a browser. Actually, after trying different tools, we end up using Streamlit. I don't know if you are familiar with this tool, but actually it's very simple. It really helps to integrate Python-based code into a web application. It has a lot of limitations in terms of what you can do in the design and setting of the general application, but at the same time, it is very powerful for basic components. And for NiChart, we decided that that was good enough for us. And one advantage of this, the cloud NiChart and installation NiChart, they run the same Streamlit code. So they are the same application. Either you run it on your desktop or on the cloud. So here, what I wanted to show is, again, I will focus on the SMRI biomarkers. We have also a lesion segmentation here. I can show it, but maybe I should focus on maybe the more interesting part of, hey, what are these biomarkers and what is the useful information coming from them? So actually, I will start from, maybe I can, okay. So here I select an existing example, like I have a demo set, demo 3. Actually, I select my ROI, so maybe I can directly go to view data because I believe this is already computed. So for this demo set, at every step, if the data is already available, it tells you, hey, I have the data. So when I go to select data, it tells me, okay, you already have data which includes the result of all processing. So this is a data set that was processed on NiChart, but I skipped the initial steps because I want to focus on the final visualization of the extracted biomarkers. But otherwise, you can push your own data and you can go through all steps. After I select my data, actually, let me show you what is the selected data. So the data now includes some demographic information that the user should enter because they are required for the machine learning packages. Then the image segmentation region. So we have 250 variables that are different regions, and we want to expand it to new segmentations, different atlases with time. And then at the very end, we have this spare scores for brain age, spare AD, hypertension, diabetes, and the serial gun scores are the brain subtype scores. And this is a set with, I think, 100 images. Yeah, this is a small set with 100 images. And in select variables, let's close this. Because there are a large number of variables, we want to select a subset of the variables. So I select the demographic columns. I add to this like diagnostic value. For this set, we have DXAD, which is AD-like atrophy. So we have control subjects and AD subjects. I want to see if AD subjects show some differentiation from the control subjects. And then I include some Muse topics. So this is a reduced set of variables from the segmentation because we have too many variables. And finally, I want to include like spare scores. We have 7 spare scores, and this set will be increased with additional models. And then serial gun, we have 5 brain aging subtypes. Okay, I selected my variables, so now our data set is reduced to a smaller set of data, and we go to the plotting. Here, the plotting is providing, like, this is, again, work in progress. We try to make this more useful while not being too cluttered. And it's a difficult task, actually. I believe the current one is a little bit cluttered because I believe I was little bit obsessed about providing a rich information, but now I see that it may be confusing. So we plan to simplify it and make it maybe layered so that the users will not get confused. But the idea is, for my data set, let's say I want to see the gray matter volume, and I want to group it by the AD diagnosis column. So this data set shows me, hey, in my data set, there are AD subjects, control subject, and MCI subjects. And actually, this is real data harmonized to the model. And what I see here is, hey, gray matter goes down with age, which I would expect. And actually, there is a clear difference in the gray matter volume in AD subjects compared to control and MCI subjects, where this gray matter change is a typical atrophy pattern that is observed in AD subjects, and MCI subjects are a mix of more AD-like or less AD-like subjects. So it's not surprising to see that they are more comparable to controls. And here we can correct by intracranial volume to make this plot normalized by the ICV, intracranial volume head size. So it is, you see the variance gets dropped, and we see now more clear pattern between MCI and control subjects. We can change the trend line because typically age-related effects are highly nonlinear. Of course, here this is a small set, so this is the lowest fit, which is pretty noisy, so it's really good to smooth it. And importantly, what we can do is here, I think this is one important benefit of NiChart. We can add centiles that show the distribution from the reference data set. So here, this is showing our distribution from the reference data set. So our objective here, and we think about how to make this data available in a better format. When you have the values, you want to understand how these values are compared to reference subjects. In this current work, we just show centiles, and you can filter them. Let's say we just want to show 25 and 75 percentile, right? So here, for example, I think it shows the AD subjects are clearly falling off under the 25 percentile, which is showing the effect of the atrophy on these subjects. And these reference centiles come from a data set, harmonized data set of over 40,000 subjects. So I think they have robust statistics. And we can add another plot here, and actually we can also select different plots here, like distribution plot, or we want to see, hey, like what is the distribution of, let's say, the total brain volume this time by the diagnosis, right? Like we can show different things, and we have some configuration to see multiple plots together. So the objective here is, hey, can we look at the data, different aspects of the data together and make sense of data? One important feature of this, again, here I have an AD subject. I click on this subject, and I want to see the image for this subject. So one thing we want to do is, and we want to do this for all image modalities. At the end, this is a mapping between the processing and the final derived data, right? So here, for example, I can see this subject had low gray matter, and I can see the image of this subject, and this tells me, hey, this subject has some atrophy. So I understand that the reason for the low gray matter is because the subject has an atrophy. And maybe now I can go to a new plot, or not distribution, but let's take a scatter plot. I want to add here a scatter plot. Let me see. Okay. Let's say I want to see the hippocampus volume, which is a typical region, which is indicative of AD-like atrophy, and also low hippocampus. Let me select it again. And each time I select a new subject, it will adapt to the image. So, hey, this subject has a hippocampus volume that is much lower, and it's a clear atrophy here. Okay, interesting. So this allows me to see my data images processing together. And I want to see, hey, what about my machine learning based biomarkers? I had a new plot, and I want to see this SPARE score. So SPARE AD was the score for AD like brain atrophy. And here I see that clearly this subject at a young age, 60 years old, have a very high SPARE AD as expected. And I'm curious, what about the brain age of this subject? Because typically, brain age is a measure of the chronological age of the subject, but it's a model trained on normal, healthy control subjects. So if I look at the brain age of this subject, yeah, this subject shows also a deviation from the group, and it has a higher brain age. What about other scores related with, let's say, hypertension? I don't know. I don't have it. It's not calculated. If you do not see it, it's not calculated for some reason. Let me check if I have the subtype. So I have, for some reason, this is not there, or there's a bug. Okay, a bug is always, Murphy's rule in a presentation is a required element, right? I don't know why it doesn't work, but I hope you get the general idea. So this panel, although looks a little bit cluttered now, I will admit, it provides you a nice way to see images, data processing together, and we try to optimize this in a way that will actually, for now, we had like some few things to make it more compact, like you hide the settings and then oops, yeah, now for this other value it gives an error. So probably if I select here, it will fix it. Yeah, now it should, or maybe okay. So I think I should not play more with this. I hope this demo was clear and it is helping you to better understand what NiChart is doing and trying to do. Okay, pediatric age range, we don't have them yet. Our focus is on 40 and above. But at the same time, we process PNC data in our lab. We have ABCD data. We want to extend this to the pediatric age. Actually, one of my earliest papers was on brain age in PNC data. And I love the challenges of pediatric data where you have so many different changes in different directions. I really want to extend it also to pediatric data, but this will take time because we try to prioritize things because there are so many different directions we can move into. As you see, even in this demo, right? Like there are things that can be improved a lot. And for this reason, again, if you can give us feedback, I will really appreciate it. And if you have any questions, please contact me or our group. We will be happy to discuss. We will be happy to provide you any type of support you may need. Thank you very much.
Thank you so much. Are there more questions from the audience? The pediatric question was going to be amongst mine, so glad Megan asked that first.
Hi, I've got a question.
Great.
Hi, I'm Sean from UCSD. I was just curious with the T2, with the lesion, white matter lesion analysis, is that a T2 or a flare?
Flare.
And also, do you envision lesion count?
Great question. Currently, what we do for lesions, we align the flare image at the end of segmentation because now we have a pure flare segmentation, deep learning based. In the past, we had flare plus T1, but current model is only flare because with deep learning, we believe this works well. But at the end, we align it to the T1 image and we calculate volumes within each ROI region. Actually, this partitions the white matter into at the lobe level, so it's not very detailed. But I think lesion count is a good suggestion. We can easily calculate it, but we don't have it readily available.
Yeah. Okay, thank
Great
you. It's really
suggestion.
great application and really useful, and I can't believe it's free. I've seen this type of stuff for sale.
Thank
But
you. Thank you.
great work.
Julia has her hand.
I don't know why. I think it's me, but I'm labeled Julia. That's very strange. Julia, did you do something to me?
Whoever's computer says Julia has a hand up and can speak. Ah,
Okay, no,
Julia,
that's
you've,
I
you've,
don't know
you've
why my
changed.
name is Julia. That's very disturbing. But thanks. That's I'm sorry because I had to miss some of the some of it. So maybe my question has already been answered in the call. But I was wondering, like, this sounds like a very integrated package, right? For the pre-processing pipelines to the visualization to exploration, machine learning aspects. So as Sean was saying, it's awesome and wonderful, like kind of a collection of things that are packaged together. What's your thoughts? What are your thoughts on how do you integrate or interact with other packages, other things that are doing part of that? So like say you wanted to visualize with knife views rather than your things. Maybe you wanted to do some pipelining with the repro containers. Maybe like
Yeah.
whatever is
Um,
there any kind of
Great
APIs
question.
or ways of integrating things or interacting with the vaster world?
Yes. Great question. As a first thing, in my opinion, in the field, there is need for more systematic integration of different tools. I think that will be for the benefit of everybody. In NiChart, currently, we didn't specifically consider how we integrate it with other tools immediately. But what we try to do, we try to design it in a way that is modular. So every component is a modular component with a clear API definition. So hopefully this will make it more easy to integrate. In the meantime, we are working with a few groups to see their structure and understand and see how we can align with it. But it has not been our main priority so far because of the items in our to-do list is very long.
Yeah.
But I really believe that integration with other tools and general integration of different tools in the field is the ultimate goal. I think that's something that should be a goal for all of us.
I agree. Thank
And
you.
I will be happy to be in touch if there are any suggestions or I will be happy to be in touch, in contact, and discuss. I will love the opportunity.
My crystal ball foresees
Thank you.
discussions of NiPoppy and NiChart someday. And the other crystal ball is, again, some of the derived properties that you are generating when they are either privately reused locally or publicly accessible, ways to integrate them with the Repro Lake types of things, the public metadata stores, so that once someone has done a process and generated some results, it's more discoverable, and of course would send them back into your data, into your interface, to deal with that, but make it more discoverable and not have to be redone. I know we're at the end of the hour. People may have to leave. At this point in time, I want to make sure to remind folks that next month, June 6th, our webinar will be Stephanie Noble here from Northeastern to talk about something from their lab. So I just want to make sure that is reminded to everybody.